Welcome to this walkthrough of LeetCode problem number 1227, Airplane Seat Assignment Probability. In this problem, we tackle a fascinating probability puzzle centered around seat assignments on an airplane. Together, we'll explore the logic and approach to solving this unique challenge. Let's get started. Let's explore the setup of this problem. You're given an airplane with N passengers and N seats, where both the passengers and seats are labeled from 1 to N. The passengers board the airplane one at a time in order. Each passenger has a specific rule they follow. If their assigned seat is available, they'll take it. But if their assigned seat is already occupied, they'll randomly select one of the remaining empty seats to sit in. There's an exception for the first passenger, who has lost their ticket and must choose a seat at random from all available seats. The question asks us to calculate the probability that the last passenger, labeled as the nth passenger, ends up sitting in their assigned seat. This is the essence of the problem we need to solve. Now, the output for this problem is a floating point number that represents the probability that the nth passenger ends up in their assigned seat. This result should be accurate to 5 decimal places. To better understand the problem, let's look at a few examples. In the first example, when n equals 1, there is only one passenger in one seat. Since passenger 1 has no other option, they will sit in the single seat available, which is their assigned seat. As a result, the probability in this case is exactly 1.00000. This is a straightforward case, as there's no randomness involved when only one passenger exists. In the second example, when n equals 2, things become more interesting. Here, passenger 1 randomly chooses between the two seats, seat 1 and seat 2. If passenger 1 selects seat 1, passenger 2 can sit in their assigned seat without any issues. This happens with a probability of 0.5. However, if passenger 1 selects seat 2, passenger 2 is now displaced and has no choice but to take the remaining seat, which is not their assigned seat. This also has a probability of 0.5. Combining these outcomes, the overall probability that passenger 2 sits in their assigned seat is 0.5, or 0.50,000. Now let's consider the case where n equals 3. Here, passenger 1 again randomly selects one of the 3 seats. 3 scenarios can occur. If passenger 1 chooses seat 1, passengers 2 and 3 can both sit in their assigned seats, so the probability for passenger 3 is 1/3 in this case. If passenger 1 chooses seat 2, passenger 2 is displaced and must randomly choose between seat 1 and seat 3. In this situation, passenger 3 has a 50% chance of getting their assigned seat. Finally, if passenger 1 chooses seat 3, passenger 3's seat is already taken, meaning passenger 3 cannot sit in their assigned seat. When we calculate the overall probability from these scenarios, we find that the result is still 0.5, or 0.50,000. This recursive pattern continues for any value of n greater than 1. The probability that the nth passenger ends up in their assigned seat remains constant at 0.5. This is because the random nature of the first passenger's choice creates an equal likelihood for displacement across all subsequent passengers. It's also worth noting some key edge cases. For the smallest input size, when n equals 1, the probability is always 1 because there's no randomness involved. For larger values of n, the process remains recursive and converges to a constant probability of 0.5. Understanding this recursive probability is the crux of solving the problem efficiently, rather than attempting to simulate every possible seating arrangement explicitly. To solve the problem of determining the probability that the last passenger sits in their assigned seat, we can first consider a brute force approach involving simulation. The intuition here is to simulate the boarding process step by step. When a passenger boards the plane, they either sit in their assigned seat if it's available, or they randomly choose another seat if their assigned one is already taken. By repeating this simulation for all n passengers and running it multiple times, we can estimate the probability based on the average outcome. However, this approach comes with significant drawbacks. While it's conceptually straightforward, the computational cost can be high, especially for large values of n. Running multiple simulations, each with O(n) complexity, results in an overall complexity of O(m*(n), where m is the number of trials. Moreover, the simulation relies on approximation, making it unsuitable when exact results are required. Therefore, while this approach provides an intuitive starting point, it's not ideal for solving the problem efficiently. A more optimized approach is to solve the problem analytically using recursive probability. Instead of simulating the boarding process, we analyze it mathematically by recognizing its recursive nature. Let's break it down. If the first passenger takes seat N, the last passenger will eventually have to sit in a random seat, which could include seat N. On the other hand, if the first passenger sits in their assigned seat, the problem reduces to the same scenario but with one less passenger and one less seat. Using this idea, we can derive a recursive formula for the probability P(n) that the last passenger gets their assigned seat. The base case is straightforward. If there's only one passenger and one seat, the probability is 1. For n greater than 1, the formula is P(n) equals 1/n plus 1/n asterisk P and 1. An interesting insight is that as n becomes very large, the probability converges to 0.5. This approach is far more efficient than simulation, with a time complexity of O(n) if we compute the recursion iteratively, and it requires only O(1) space to store the intermediate results. It's elegant, precise, and works seamlessly for large inputs. Given the options, the recursive analytical approach emerges as the best strategy for solving this problem. It combines mathematical precision with computational efficiency, avoiding the pitfalls of the brute force simulation. By leveraging the recursive formula, we can compute the exact probability in O(n) time, making it suitable for large values of n. In comparison, the brute force simulation, while simple to implement, is computationally expensive and only provides approximate results. This makes it less reliable, especially when exact answers are required. The recursive probability method, on the other hand, is not only efficient but also provides a deeper understanding of the problem structure. For this reason, it's the preferred approach, balancing precision, efficiency, and scalability effectively. In this problem, we're tasked with calculating the probability that the last passenger on an airplane sits in their originally assigned seat. Here's the scenario: n passengers are boarding a plane with n seats. The first passenger loses their ticket and randomly picks any seat. Each subsequent passenger will either sit in their assigned seat, if it's available, or randomly select one of the remaining seats. The key insights here revolve around the recursive nature of the problem and the concept of probabilistic symmetry. First, if the first passenger happens to pick their correct seat, the problem is immediately resolved, and the last passenger will sit in their assigned seat. Alternatively, if the first passenger picks any other seat, the problem reduces to a smaller instance with one fewer passenger in seat, following the same rules. Additionally, the symmetry of the problem simplifies things. Regardless of the intermediate choices made, the probability of the last passenger sitting in their assigned seat remains consistent. These two insights form the foundation for solving this problem efficiently. Now, let's explore the base cases and the formula that emerges from this problem. For n equals 1, the probability is straightforward. Since there's only one seat, the first and last passenger are the same, so the probability is 1. For n equals 2, the first passenger has an equal chance of sitting in either seat, meaning the probability is 0.5. From this, a general formula can be derived to calculate the probability for n passengers. The formula can be written as P(n) equals 1/n plus 1/n asterisk P and 1 plus 1/n asterisk P and 2 plus 1/n asterisk P 1. While this formula looks complex, symmetry in the problem allows us to simplify it drastically. For any n greater than or equal to 2, the probability stabilizes at 0.5. This reduces our problem to just understanding this inherent symmetry and applying it mathematically. The algorithm itself can be broken into a few simple steps. First, recognize that for n equals 1, the probability is 1. Then, for n equals 2 or greater, the symmetry leads to a constant probability of 0.5. This conclusion eliminates the need for iterative or recursive calculations. To derive this result more intuitively, let's break it down further. The first passenger randomly chooses one of n seats. If they choose their own, the last passenger's seat remains untouched, and the probability that the last passenger sits in their assigned seat is 1. However, if the first passenger chooses another passenger's assigned seat, say seat K, the problem reduces to n1 passengers and seats, with the same rules applying. By carefully analyzing this recursive structure alongside the symmetry in the problem, we find that the probability remains constant at 0.5 for all n greater than or equal to 2. This insight allows us to optimize the calculation. Instead of iterating through the recursive formula or simulating the problem for different values of n, we directly use the result that p, n, equals 0.5 for all n greater than or equal to 2. The implementation becomes straightforward. For n equals 1, return 1, and for n greater than or equal to 2, return 0.5. This approach avoids unnecessary computations and leverages the mathematical properties of the problem. Additionally, no complex data structures are required since the solution is purely analytical. Next, let's analyze the complexity of this solution and address potential edge cases. First, the time complexity of the solution is 1. This is because determining the probability involves a simple constant time check of whether n equals 1 or is greater than 1. Similarly, the space complexity is 1, as no additional memory is allocated, everything is calculated directly from the input. For edge cases, consider small values of n. When n equals 1, there's only one passenger and one seat, so the last passenger will always sit in their assigned seat, giving a probability of 1. When n equals 2, the first passenger's random choice equally splits the outcomes, resulting in a probability of 0.5. For large values of n, the result consistently remains 0.5 due to the symmetries we've discussed. Finally, invalid inputs, such as when n is not a positive integer, should be addressed by returning an error or a default value to ensure the function handles all possible scenarios robustly. With all the insights and analysis in mind, the final solution is remarkably simple. Here's the implementation. We define a function called seat_probability that takes n as input. If n equals 1, the function returns 1.0, as the last passenger will always sit in their assigned seat. For any other value of n, the function returns 0.5, leveraging the symmetrical behavior of the problem. This implementation is efficient, concise, and mathematically sound, providing the correct result in constant time. By directly applying the derived probability formula, we avoid unnecessary complexity and ensure the solution is both elegant and optimal. This is a concise Python implementation of the solution to LeetCode problem number 1227, airplane seat assignment probability. The problem requires calculating the probability that the last passenger gets their originally assigned seat in an airplane scenario. The function nth person gets nth seat takes a single integer input n, which represents the number of passengers and seats on the airplane. 1. The first condition checks if n equals 1. If there is only one passenger, they have no choice but to sit in their assigned seat. Thus, the probability that the last passenger, who is also the first in this case, gets their assigned seat is 1.0. 2. For cases where n is greater than 1, the function directly returns 0.5. This is based on the mathematical insight that for any n greater than 1, the probability converges to 0.5 due to the recursive nature of the problem. Whether the first person randomly picks the last seat or not, the recursive probabilities always simplify to 0.5 after all passengers have seated. The implementation is efficient, running in 1 time complexity since it involves only a couple of conditional checks and no loops or recursive calls. This makes the solution optimal for any input size. This is the Java implementation of the LeetCode problem number 1227, airplane seat assignment probability. The logic mirrors the Python implementation exactly. If there is only one passenger, the probability is 1.0 since they must sit in their own seat. For all other cases, the probability converges to 0.5. The key difference lies in Java's class structure and type declarations, which are explicitly defined here. In this problem, we need to calculate the probability that the nth person gets their assigned seat when boarding an airplane. The twist is that the first person chooses a seat randomly, and every other person either takes their assigned seat if it's available or selects randomly from the remaining seats. Let's start with the simplest case where n equals 1. If there's only one passenger, they have no choice but to sit in the only available seat, which happens to be their assigned seat. This means the probability is 1.0. The code handles this case directly by checking if n equals 1 and returning 1.0 immediately. This is straightforward because there's no randomness involved when there's only one passenger. Now let's analyze the case where there are two passengers, n equals 2. The first person, person 1, chooses randomly between the two seats, seat 1, which is their assigned seat, and seat 2. There are two possible outcomes here. In the first outcome, person 1 chooses seat 1, their assigned seat. This leaves seat 2 for person 2, which is also their assigned seat. In the second outcome, person 1 chooses seat 2. Now person 2 is forced to take seat 1, which is not their assigned seat. Since each outcome is equally likely, there's a 50% chance that person 2 gets their assigned seat. The code generalizes this logic for any n greater than 1 by returning 0.5 as the probability. Let's extend this to n equals 3, with 3 passengers. Person 1 starts by choosing randomly among the 3 seats, seat 1, seat 2, or seat 3. If person 1 chooses seat 1, their assigned seat, then both person 2 and person 3 will also get their assigned seats, making the probability for person 3 to be in their assigned seat 100% in this scenario. If person 1 chooses seat 2, person 2 is forced to choose randomly between seat 1 and seat 3. Here, there's a 50% chance that person 3 ends up in their assigned seat. Similarly, if person 1 chooses seat 3, the situation becomes symmetric to the previous case, and again there's a 50% chance that person 3 gets their assigned seat. Combining these outcomes, the overall probability for n equals 3 is 0.5. This result illustrates a key property: for any n greater than 1, the probability stabilizes at 0.5 due to the symmetry in the problem. The key insights from this problem are as follows. When n equals 1, the solution is simple and deterministic. The probability is 1.0 because there's only one seat. For any n greater than 1, the problem can be understood recursively, but the outcome simplifies to 0.5 because of the symmetry in the seating choices. The code leverages this observation efficiently, avoiding unnecessary computations and directly returning 0.5 for all cases where n is greater than 1. This insight is what allows the solution to be both elegant and computationally efficient. Here, we analyze the time complexity of the solution for problem number 1227. The algorithm is incredibly efficient, with a constant time complexity of 1. First, the function checks if the input n equals 1. This is a simple comparison operation that takes constant time, regardless of the value of n. Next, based on the input, the function immediately returns either 1.0 or 0.5. This return statement is also a constant time operation since it does not depend on the size of the input. With no loops, recursion, or input-dependent calculations, the solution executes in a fixed number of steps. As a result, the time complexity is 1, making it highly optimized and predictable in performance. Now, let's consider the space complexity of the solution, which is also 1. The reasoning here is straightforward. The input is a single integer n, which occupies constant space in memory. Additionally, the algorithm does not create any auxiliary data structures, arrays, or lists that would consume more memory as n increases. Even the return value, which is either 1.0 or 0.5, is a floating point number that takes up constant space. Since no memory usage scales with the input size, the space complexity remains 1, ensuring that the solution is both time and space efficient. To appreciate the efficiency of the given solution, let's compare it with a brute force approach. A naive method might involve simulating all possible seating arrangements for n passengers to calculate the probability of the nth passenger getting their seat. This would require generating all permutations, resulting in an n time complexity due to factorial growth. Alternatively, a recursive simulation could explore all possible seating decisions, leading to an exponential time complexity of 2 to the power of n. However, the provided solution avoids these computationally expensive methods by leveraging a mathematical insight, where for n greater than 1, the probability stabilizes at 0.5. This eliminates the need for simulations or iterations, bringing the time complexity down to 1. The constant time complexity of this solution is rooted in a key mathematical insight. For n equals 1, there is only one passenger, so the probability of them sitting in their assigned seat is 1.0. For n greater than 1, the problem simplifies due to symmetry in the seating arrangements and the recursive nature of the process. When the first passenger chooses a seat, there are 3 possibilities: they choose their own seat, the nth seat, or any other seat. If they choose their own seat, the probability of the nth passenger getting their seat is 1/n. If they choose the nth seat, the probability is 0. For all other seats, the problem reduces to a smaller instance with the same probability of 0.5. This symmetry allows us to conclude that for n greater than 1, the probability stabilizes to 0.5, which the solution directly returns in constant time. This elegant reasoning underpins the O(1) time complexity. Here are some common mistakes to watch out for when solving this problem. First, many people misinterpret the problem statement. The first passenger's random choice is not just an isolated event, it influences the entire sequence of seating decisions for the subsequent passengers. This cascading effect is critical to understand. Next, overcomplicating the problem can be another pitfall. Some attempt to simulate all possible seating arrangements, which is computationally expensive and unnecessary. Instead, the problem can be tackled with a mathematical approach that avoids brute force simulations. Additionally, overlooking base cases like when there's only one passenger can lead to incorrect solutions. Always check that your approach handles these simplest scenarios correctly. Another mistake is assuming symmetry in the probabilities. For instance, some believe that the probability of the last passenger sitting in their assigned seat is always 50%, regardless of the number of passengers. This is incorrect. The probability must be calculated using proper reasoning. Lastly, while rare for this problem, it's important to be mindful of floating point precision, especially for very large inputs. Ensuring your calculations remain precise is a good habit to develop for handling edge cases in general. Now let's discuss some insights for interviews. One key focus should be on deriving the formula. Interviewers are often more interested in your thought process, how you identify patterns and simplify the problem, than in the final answer itself. Be ready to clearly explain the reasoning behind your probability calculation. Another important factor is how you handle edge cases. For example, demonstrating that you've considered cases like when n equals 1 or 2 highlights your attention to detail. It's also worth emphasizing why brute force approaches are suboptimal. Showcasing an optimized, mathematical solution will not only save time but also earn you extra points for efficiency. Since deriving the solution involves recognizing recursive patterns, practicing recursion and mathematical induction can help you articulate your thought process more effectively. Additionally, exploring related problems can deepen your understanding. For instance, problems like best sightseeing pair or stone game require identifying patterns and making optimal decisions, while Pascal's triangle involves recursive reasoning and combinatorics. These connections can strengthen your overall problem-solving skills. Finally, let's break down the key insights and patterns. The most important takeaway is that the probability of the last passenger sitting in their assigned seat is always 1/2, as long as the number of passengers is greater than 1. This conclusion is derived mathematically by analyzing the recursive relationships that govern seating probabilities. To understand this, think about the first passenger's choices. They can either sit in their own seat, take the last seat, or occupy another passenger's seat, which creates a chain reaction that continues until the last passenger boards. By simulating small cases, such as when there are 2, 3, or 4 passengers, you can see the pattern emerge. Recognizing this pattern quickly is a valuable skill, especially in a high-pressure interview setting. Ultimately, this problem exemplifies how mathematical insight and probability theory can simplify seemingly complex challenges. Instead of relying on computational brute force, focus on understanding the underlying relationships and deriving a general formula. This approach not only saves time but also demonstrates a deeper level of problem-solving expertise. Thank you for joining me on this walkthrough of LeetCode problem number 1227. We summarized the mathematical insights, the simplicity of the solution, and the importance of understanding probability-based problems. Don't forget to like, share, and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!